let's go ahead and look at applications of the equilibrium constant. So based on our value of K, we've been able to establish that, if we have K values that are much greater than 1, then our reaction lies towards the products. Okay, and we also know that if K is much smaller than 1, okay, it's going to lie towards the reactants. Okay, so we've already talked about that and established these facts in our previous lecture. Now, I want you guys to understand that the time it takes to reach equilibrium is not related to K. So remember that the time it takes for equilibrium to be reached is going to be based on the reaction rate of the specific reactions you're looking at, and that's subsequently dictated by your activation energy. So remember, okay, that activation energy and the transition between reactants and products, that's what is affecting the rate of the forward and reverse reactions and subsequently affecting the time it takes to reach equilibrium. Okay, now the size of K, we've talked about the fact that it doesn't have any units and all of those types of things. And so the size of K is actually determined by those activities or those thermodynamic factors that we're going to discuss a little bit later. Okay, so the extent of the reaction, we understand that the greater K is, the more products we're likely to get. The smaller K is, the more likely we're going to have more reactants in that mixture. Okay, and basically we've now talked about the fact that the time it takes to reach equilibrium is dictated by the size of EA, okay, and that the size of K is determined by those thermodynamic factors that we'll discuss later. Okay, so we understand that K can tell us, the extent to which a reaction proceeds. Either we're going to have mostly products or mostly reactants based on the size of K. However, we can use something called the reaction quotient, which is Q, to tell us a few other things. Okay, so the reaction quotient Q can help us determine if a reaction is at equilibrium or if it's not. Okay, it can also help us decide which direction the system needs to move in order to reach equilibrium. Okay, so we're going to use basically a modified version of our equilibrium expression, and instead of using K and concentrations of our reactants and products at equilibrium, we are going to use Q to represent the reaction quotient, and we're going to use initial concentrations of our reactants and products to solve for Q. Okay, and then we're going to take our Q value and subsequently compare it to our K value, and that can answer a ton of questions for us. So when we do the comparison of Q and K, depending on how their numerical values relate, is going to dictate whether the reaction system needs to shift towards products or towards reactants, or if you're in fact at equilibrium. Okay, so if we look at this first situation here, when the reaction quotient is smaller than K, that means that the ratio between the initial concentrations is too large. Okay, so in that case, the system is going to shift towards the right or towards the products in order to obtain equilibrium. Okay, if your Q value is equal to K, the system is at equilibrium. So there's no shift needed in order to reach equilibrium because you're already there. Okay, and finally, if Q is greater than K, that means that the ratio between your initial concentrations is too small. So your system needs to shift to the left or towards the reactants in order to reach equilibrium. Okay, so if we compare our Q value to our K value, we can basically figure out what needs to happen in order for equilibrium to be reached. Okay, so in this question here, they've asked us to predict the reaction direction. Okay, so they've given us a reaction. Okay, they've given us an equilibrium constant, and they want us to tell them which direction the system is going to shift. Okay, so first thing we want to do is we want to write our equilibrium expression, except we're going to write it with respect to Q and our initial concentrations, because we already have K, and what they've given us down here, notice, are concentrations not. Okay, those concentration nots indicate that those are initial concentration values for each of those items. So we're going to write an equilibrium expression or reaction quotient expression as follows. Okay, so QC is going to be equal to the concentration of NH3 squared over the concentration of N2 and the concentration of H2 cubed. Okay, so now that we have our reaction quotient, we can use this equation, okay, and the initial concentration values that they've provided us here to subsequently calculate our Q value. Once we calculate our Q value, we're going to compare that Q value to the K, and depending on if it's bigger or smaller or even equal to the K value, that's going to dictate the direction of the shift. Okay, so let's go ahead and let's do this first example out for A. Okay, so my QC in terms of the condition seen in A is going to be 1 times 10 to the negative third. Okay, this is going to be squared divided by 1 times 10 to the negative fifth, okay, to the first power, okay, times 2 times 10 to the negative third cubed. Okay, and we're going to go ahead and plug that into our calculators. And that's going to give us the following. Okay, so that's a pretty large Q value, as we can see. So in the case of A situation, Q is much bigger than K. So what that means is that the amount of products is too large, okay, and equilibrium has not been established. So in order for this reaction, given the conditions here, to reach equilibrium, okay, you're going to have to shift to the left, okay, or towards your reactants. So if we go ahead and plug in the initial concentration values for the situation seen here with step B, or question B, we're going to see that our Q value is going to be equal to 0.60. Okay, and if QC in this case is 0.060, excuse me, that means that K is equal to Q. And in this case, okay, you are at equilibrium. So if we go ahead and take a look at the last set of data, okay, and plug it into our reaction quotient as seen here, okay, just like we did in the previous examples, we get 0.002. Okay, so in this case, QC is smaller than K. Okay, and in that case, what that means is that the relationship between reactants and products, there's too many reactants present. So what's going to actually happen is you're going to shift to the right in order to balance that out, and basically you're going to go towards the product side. Okay, so once again, what you're going to do here in these types of questions, okay, you've been given K, you've been given a balanced equation, you write your reaction quotient with respect to your molar concentrations in the same way you'd write your equilibrium expression with respect to K. The only difference here is instead of using equilibrium concentrations, you're going to actually be using initial concentrations. You go ahead and plug those initial concentrations into your reaction quotient, and then you subsequently compare your value of Q to your value of K. And depending on how they're related, okay, you can establish if you need to shift towards reactants, shift towards products, excuse me, or basically if you are in fact at equilibrium. So let's go ahead and take a quick look at calculating equilibrium concentrations. I want you to notice that they've given us an overall equation here. They've given us our equilibrium constant. They've given us partial pressures of some of the components of our above reaction at equilibrium, and they want us to calculate the partial pressure of NH3 at equilibrium. So in this problem, what we're going to do is obviously write our equilibrium expression. Notice they're asking for partial pressures, so we're going to write this with respect to Kp. And then go ahead and write our equilibrium expression with respect to our partial pressures. So PNH3, okay, I'm going to put parentheses around that, squared, okay, partial pressure of N2, okay, and partial pressure of H2 cubed, okay, and then let's go ahead and look at what we know. Okay, so we know our Kp value that was given to us we know our partial pressures of N2 and H2. Okay, so then we can subsequently figure out our pressure of NH3. So really what we have here is we have our equilibrium values for each of the following. Okay, that's what's been provided. Okay, so at equilibrium, okay, we know that we have 0.432 ATM, okay, 0.982 ATM, okay, and the partial pressure of NH3 is actually what we're solving for. Okay, so we can actually plug these values into our equilibrium expression. So Kp is going to equal x squared over 0.432 to the 0.982 cubed. Okay, so we also know our Kp value, right? So that's actually all going to be equal to the following. Okay, so we're going to manipulate this out, okay, to give us x squared being equal to 5.93 times 10 to the negative 6th. Okay, and we take the square root of both sides, and x is going to subsequently equal 0.00243. Okay, and K is therefore, P of NH3 is therefore this in ATM. Okay, so please ignore what I have over here. All right, and that's basically how we approach a problem like this. It's pretty straightforward, it's just basic math, plugging and chugging those numbers and solving for the appropriate variables. And if you want to check your answer, you can always take your newly found pressure values along with the original two at equilibrium, plug them into your equilibrium expression, and you should subsequently get the equilibrium constant that you see here. Now, here's an expanded approach to this problem that will basically allow us to utilize information from our initial concentration values that we've been given. So this is going to require some ice table work and things of that sort. Okay, so in this problem we've been told that we have this chemical reaction here. We're told that we have a 1 liter flask and it's filled with 1 mole of hydrogen and 2 moles of iodine. Okay, and we've been given our K value. They now want to know what the concentrations are of H2, I2, and HI at equilibrium. Okay, so in this problem, obviously the first thing we want to know is our concentration values and things of that sort. Okay, so we're going to write out the ice table for the reaction that we're going to be looking at. So H2 plus I2 gives you 2HI. Okay, and then go ahead and write that out here. Our initial concentrations, we've been given these values with respect to moles of each of the gases in a 1 liter flask. So our first reactant's concentration is 1 mole divided by 1 liter, which is going to give us a concentration 1.0 molar. Okay, our I2 is 2 moles of iodine in the 1 liter flask, so we're going to have this concentration of I2, and obviously initially we're going to have 0 concentration of HI. Okay, so now we need to analyze how this reaction is going to change. Okay, remember we consider the coefficients when we establish this. Okay, so in the case of H2, there's 1 equivalent, and we know that the amount of reactant is going to decrease, so minus X. Same thing with I2. Okay, and we know that that will produce 2 equivalents of HI, so we're going to have a positive 2X here in our change situation. Okay, so when we go ahead and write out our equilibrium setup, we're going to have 1.0 minus X. Okay, we're going to have 2.0 minus X. Okay, and we're going to have 2X for our concentrations at equilibrium. Okay, now remember, we've been told that our K value is equal to 50.5. Okay, and we have a balanced equation, so we can write an equilibrium expression as follows. We'll go ahead and do that really quickly, because we'll be using it here in a second. Okay, H2 and I2. Okay, And what we're going to do now is we're going to subsequently plug in our values at equilibrium into this equilibrium expression. Okay, so our Kc is going to be equal to 2x squared divided by 1.0 minus x, okay, times 2.0 minus x, right? Okay, and this is what our Kc, which is 50.5, is all equal to. So you're going to go ahead and FOIL these two down here, and then multiply this number by what we got from our foiling process, and that's going to be equal to 2x squared. We're then going to put everything on the appropriate sides and set it equal to 0. Okay, so we're going to go ahead and do that real quick. Let's see. We will have 4x squared on top, okay, and on the bottom, when we FOIL this out, okay, we're going to get x squared minus x, okay, plus 2, right, and that's going to all equal 50.5. Okay, we go ahead and cross up and multiply out. Okay, that's going to subsequently give us 4x squared is equal to 50.5 times x squared minus 0.0x plus 2.0. Okay, and then if we multiply through all of these and subsequently bring everything over to the left-hand side, we will end up with 46.5 x squared minus 151.5x plus 101.0, all equaling 0. Okay, so now that we have a equation, we can subsequently use the quadratic equation in order to solve for x. Okay, so minus b squared plus or minus the square root of 4ac all over 2a. Okay, so remember this right here is a, this right here is our a, this right here is our b, this right here is our c. Plug them into the appropriate equation. Okay, and when you solve it using the quadratic equation, okay, you're subsequently going to get two answers, right? You're always going to get 2 because you're doing this plus or minus portion on your quadratic. So what you're going to go ahead and do is you'll get two answers. Okay, you'll get 2.323 or 0.935. Okay, and when you get these two answers, what you're going to do is you're going to then take them and plug them back into the concentration values for equilibrium. Okay, so if we look at plugging in 2.323, notice that you're going to end up with negative concentration values. Okay, we know that negative concentration values are not an option. Okay, so because of that, that's not an acceptable value to plug in. So in this situation, the acceptable value to actually plug in is your 0.935. Okay, so if I take that 0.935 and subsequently plug it back into my equilibrium concentration values, I'm going to get 1 minus 0.935. That's going to give me my concentration of H2, which in this case is going to be 0.065. Okay, my concentration at equilibrium of my I2 is going to be 2 minus 0.935, which is going to give me 1.065, right? And then the concentration of my NH3 is just going to be 2 times 0.935, which is going to give me 1.87. Okay, so I've taken the value here that we solved from the quadratic equation, the only one that makes sense, and plugged it back into these concentration values. Okay, and then of course I can always go back and check my answers. I can take the concentration values that I got at equilibrium, plug them into my equilibrium expression, and I should get the value that I would anticipate getting based on what I was given. Okay, so in this case, guys, we're going to look at treating systems with very small k values. So in this situation, we've been given a balanced equation. We've been given an equilibrium constant, and we've been told what our initial concentrations of our reactants in this case are. Okay, and basically they want us to calculate what the equilibrium concentrations are. So the first thing that we need to go ahead and do is set up our ICE table. So as you can see here, I've set up my ICE table. We have our initial concentration of NaCl. We took that 1 mole divided by 2 liters. Okay, and our initial concentrations of our products are 0 and 0 respectively. Okay, now the change that we anticipate, remember, is going to be dictated by your coefficients. So minus 2x, because I have that coefficient of 2 in front, and the fact that it's a reactant, it's going to get used up. Okay, NO is going to be produced, so it's the positive sign. There's a coefficient of 2 in front of it, so it's 2x. And Cl2 has a coefficient of 1, so x is the value that we see here. Okay, so then we utilize our initial and change values to set up our equilibrium concentration values with respect to x. So you bring them all down like you've seen here. Okay, and then we take these values, just like we did in our previous example, and we plug them into our equilibrium expression. Okay, so we have them as follows. So if we look at the numbers that have been provided in this equilibrium expression and the concentration values, you quickly notice that you'd end up with some sort of cubic function, right? Okay, sorry, your 2x squared times x. Okay, that's going to give you a cubic function. Now that doesn't work out really great with respect to solving using the quadratic equation. So in order to basically deal with that in a simplistic way, we can take advantage of the fact that our equilibrium constant is very small. So basically, assuming that k is so small, allows us to drop this portion of our calculation. Okay, so the reason why we can drop it here is what we're saying is that basically the equilibrium constant is so small that the change in concentration of your reactants upon reaching equilibrium is very tiny, so it's a negligible thing and basically leads to something we can ignore. Okay, so instead of plugging in 0.5 minus 2x, we're just going to plug in the 0.5 value. Okay, once again, we know our Kc, we know our other concentration values with respect to x. Okay, plug in our 0.5, and that's subsequently going to give us 4x cubed divided by 0.5 squared, all equal to 1.6 times 10 to the negative 5th. And that's going to give us 4 times 10 to the negative 6th, okay, all equal to 4x cubed. Okay, we're going to go ahead and divide out by 4. Okay, and that's going to give us 1 times 10 to the negative 6th, okay, is equal to x cubed, right? And basically we get rid of that x cubed by taking the cubed root of both sides. So our x value is going to equal 0.01 or 1.0 times 10 to the negative 2. Okay, so this is what we've calculated. Now, before we can accept this approximation, we need to go back and check if the approximation is valid. Okay, so what you're going to do in that situation is you're going to go back and you're going to plug in that x value, okay, into your equilibrium concentration. So in this case, 0.5 minus 2 times 0.01, okay, and that's going to give you 0.48 as your concentration at equilibrium. Now I want you to notice that that value is actually only 0.02 off of the 0.5 that you would have assumed was present when you dropped that x. Okay, so then what you're going to do is you're going to take that 0.02 and divide it by 0.5, okay, and multiply it by 100, and that's going to give you your percentage that value is off. And so basically, if you're at 5% or below in terms of how off it is, the approximation is acceptable, and you can use this methodology to calculate your X values.